A large hospital wants to figure out whether the mean wait time differs between patients who come in on an ambulance and patients who are driving themselves. And so they do this by looking at a random sample of 150 patients with heart attack symptoms. And they figure this out and get their mean wait time and standard deviation of the wait times for ambulance and all of that. And so what would happen if using a 99% confidence interval, we figure out like what the mean difference in the wait times is between the ambulance transported patients and self-transported patients. So the way that we would do this to find a 99% confidence interval is PANTS. And so PANTS is basically an acronym that explains the different steps of finding confidence intervals. So the first thing we need to say is the proportion. So what are we finding? We're finding the proportion of difference in mean between between wait times of ambulance transport patients and self-transported patients. And so then we have to go to the assumptions. So what are we needing to assume in order for us to proceed and see this is about a normal approximation? So we need to assume that this is a random sample, and it states that this is a random sample of 150 patients. We also need to figure out that it's approximately normal, and using the central limit theorem, because our sample sizes are 77 and 73, these are both greater than 40, and so using the central limit theorem, we can say that these are approximately normal. The next thing we need to do is we need to name the test. And so important things also to do is we need to look at, well, what data are we given? And we're given that the mean of the sample of people who come in from the ambulance is 6.04 minutes, and that the mean of people who are coming in from this self-driven is 8.3. And the standard deviation of people who are coming in by ambulance is 4.3 minutes in wait time, and the standard deviation of people who are self-driven is 5.6. And so if we're trying to find a 99% confidence interval, the interval we need to use is a 2-sample t interval. And so why are we using a 2-sample t interval? Well, we're using a 2-sample t interval because we're given 2 sets of data. We're given the ambulance and the self. And we're using a t interval because we don't know the standard deviation of the entire population. We only know the standard deviation of the samples. So then we have to use t. Part is the t, and so this is to actually test the equation. And so this is the equation we have. We have the mean of ambulance minus the mean of self-driven plus or minus t star times the square root of the standard deviation of the ambulance squared all over the sample size plus the standard deviation of the self-driven squared all over the sample size. And so when you plug this in, if you follow this equation, we get 6.04 minus 8.3 plus or minus 2.66. Well, where do we get 2.66? We get this from our t-chart. And so what we do is we have to find the degrees of freedom. And the degrees of freedom can be found by taking the minimum population size, which is 72, and subtracting, it's 73, and you subtract 1, which means that our degrees of freedom is 72. But because we're using a chart, we have to round down, and so we have to go to 60. And we're looking for a 99% confidence. So we scroll over to 99% confidence. And if we're looking at 60, we get 2.660. Right there, it's circled. 2.660. So we plug in that for t star, so 2.660, and then we do the square root of 4.3 squared all over 77, because 4.3 is the standard deviation, and then 77 is the population size, plus 5.16 squared all over 73, because that's the sample size. And then we end up with negative 2.26 plus or minus 2.168, and that gives us an interval of negative 4.317 to negative 2.023. Last part of PANTS is to put the statement in context. And so if we're looking at the interval, it's basically saying that we are 99% confident that the true proportion of the difference in the mean wait times between ambulance transported patients and self-transported patients is between 0.2 minutes and 4.3 minutes. So they're waiting about 0.2 minutes to 4.3 minutes. Say that someone wanted to figure out if the difference in the mean wait times is statistically significant based off of this confidence interval. Well, the way to do that is by using phantoms. So statistical significance is found by phantoms, and it's the same. A lot has the same portion. So P is the proportion. We're looking at the same proportion as we found previously. H is the only difference. H is where we state our hypotheses. So we have our null and our alternative hypotheses. So our null is, we're assuming that the wait time between somebody coming in from an ambulance and somebody coming in from self-care is equal, so that if we subtracted these, they would equal 0. But then we're seeing, well, what if they're not equal? And so that's what we're testing. And so then we have to go to then our assumptions, which are the same. We say that it's random, and it's also using central limit theorem. We assume that's approximately normal. And then we go to naming the test, and we're doing a 2-sample t-test. So it's the same thing as the 2-sample t-interval, but this time it's a test. And we're doing the t-test because we don't know the standard deviation of the population, only of the sample. And so then you have to actually test the interval. And this is the equation that we're given. And so when we plug in, we're using the same information from up here. And we plug in 6.04 minus 8.3 minus, you see that they're subtracting the means of the population. And so we're just going to put 0. We're assuming there's 0 over. You plug in 4.3 squared over 77 plus 5.16 squared over 73. And that gets you negative 2.9 for your t value. And so then if you go ahead and plug it into the calculator, you can't really see it right now. Oh, there we go. We've got a 2-sample t-test. And so if you plug in all this data, you can find P, which we find to be 0.004. And so if P is 0.004, no matter what alpha level we're testing at, but we're going to test at 0.01, we see, so that's the next step. O is you're actually going to name your alpha level. And we know that the alpha, or not alpha level, P score. So your P is 0.004. Well, now we have to compare, that's the last thing, M, to the alpha level. And so we're going to use an alpha level of 0.01. And 0.004 is less than 0.01. Alpha level of 0.01, we can actually reject the null hypothesis, pardon me, because P is less than. And so there is enough statistical evidence to suggest that the wait times between ambulance and self-driven people is different, and that it's not the same. And so using that, we can say, well, based only on the confidence interval is 99%, and it's saying that 99%, that we are 99% confident that it lies between, that the mean difference lies between a wait time of 0.2 minutes and 4.3 minutes. And we're saying here, in the null hypothesis, we're claiming that it's 0. But if we are 99% confident that it lies between 0.2 minutes and 4.3 minutes of a wait time, then 0 is not included in that. And so therefore, it is statistically significant. The difference in the mean wait times is statistically significant because the null hypothesis does not lie inside of it, and the alternate does. And so the null hypothesis is HA equals HS, and that's not going to be true because that's assuming that the wait time is 0, and that does not lie within our confidence interval. Pants and phantoms are important when we're trying to compare how statistically significant data is and also how confident we are on data. And this can be done for data that gives us proportions. It can be done for sets of data that give us one sample. There are multiple different tests that we can use. and it helps us solve problems such as these to see differences in data.